Okay, thank you, Giulio. So, like Giulio said, the idea of IIT is to explain contents of experience starting from space. I'm not going to be able to do justice to the depth and all the details and the richness and the complexity of the explanation that was developed for the space paper. If you are interested, you can check out this paper that came out in 2019 in Entropy. And also, I invite you to all to consult the unfathomable richness of seeing article that has been uploaded to archive recently that expands on the space paper to actually address the aspect of richness when we see things in space, such as dots or complex scenes. I want to start just taking one step back and reminding you of what the main idea of IIT and methodology of IIT is. So Giulio showed that for IIT, there must be an identity between an experience and all the distinctions and relations that compose it, the phenomenal distinctions and relations, and a cause-effect structure on the right side, which is also composed of causal distinctions and relations. So when we talk about this identity, we're talking about an identity between a full experience, which is a moment of consciousness. Right now, you see the screen, you hear my voice, you maybe have the taste of coffee in your mouth, this whole thing, which is the broad qualia, like discussed by now, and then a full cause-effect structure. When we address the quality or the content of experience, most likely what we're trying to do is to take a component or a set of components or an aspect of experience, in this case, the extendedness of visual space, and find a substructure within the whole cause-effect structure that would have properties that correspond to the properties of this aspect of phenomenology. So the idea here is to describe the phenomenology of visual space in detail, and then unfold a substrate that is not the main complex, is not the whole, let's say, substrate that contributes to consciousness, but just one subset of it that contributes this specific content of experience, which is in this case space. I will come back to this picture later to talk about the substrate, but first, what do we mean when we talk about space? This is a hard task, and it's going to be a little embarrassing maybe to try to show you what we mean. It will be superficial and rather short, but bear with me, just an example to really understand each other. Of course, we are not talking about the space that is out there, that physics describes, that has many properties. We're talking about the space of our experience. We're talking about the fact that when you look at the screen right now, you see an expanse that is dark, but it's still there in front of your eyes, right? Now, this space, if it's accounted for with tools of IIT, the idea is that it is going to be structured because all quality is structured for IIT, and it is going to be described in terms of phenomenal distinctions and phenomenal relations. First of all, I want to clarify that when we abstract the aspects that make space feel the way it does, we're not really talking about the content of the space, whatever we observe on the screen. So for instance, the screen, of course, could be red, or it could be green, could just be black. The space is still there. It doesn't really depend on what's on the screen, on the local qualities that Giulio mentioned. And this is crucial because the experience of the extendedness of space that we want to characterize is the one that is still there, even if you were to close your eyes, like you're still having the feeling of an extended canvas. In this case, it's just dark. So there are various properties of the extendedness of space that we want to characterize. And besides being independent from the color of the canvas, are also independent on the fact that there are objects. You constantly see objects, like in this case, you could be seeing a face, you could be seeing a house, they would all be located in space, but again, the space is still there, even when there is nothing on the screen, so to speak. So, as I said, the IIT method describes contents of experience in terms of distinctions and relations as a structure of distinctions and relations. And the idea is that we can characterize space. Well, this is just a summary point. There is something it is like to have a spatial experience irrespective of the colors, objects, and sensory stimuli you are experiencing. So what are the properties of space that we start from when we characterize it in phenomenal terms? What are these distinctions and relations in phenomenal terms? Or roughly speaking, you can think about distinctions in your experience of space as the fact that there must be a lot of components that you're experiencing at all times for space to feel the way it does. And here, just as an example, you see a spot on the screen, right? There's a bright spot. It's there on the screen. You see this region highlighted from the rest of the space. But if the spot goes dark, the space doesn't disappear. The spot, so to speak, is still there. It's just dark, right? It's not bright anymore. And this is true if I show a lot of spots on the screen, they are now still there. You're still seeing the screen as extended. All those regions are still there. They're just like dark. This is a first important point we want to make. In order for space to feel the way it does, there must be a lot of distinction. They must all be there. Another way to really just an intuition pump to understand what we mean is that if I now have two bright spots at a specific distance and I'm focusing on the region of space between these two bright spots, the claim is that there's a lot of spots there that you must be experiencing for that region, that column to feel extended. What would happen if there were no spots in that region, neither bright spots nor dark spots, if you just didn't experience anything in there, no components of your experience were filling that part? Well, we can represent it as showing how can you possibly experience that these two bright dots are at a distance? There will be no space between those two dots, right? This is again just a representation. We can sort of think about losing space because there are no components to that substructure of your experience. So a second crucial point in the analysis of space is that to experience space, you must be experiencing countless spots. If you think about the whole canvas, there must be a lot of spots that you're experiencing at all times. But if we go back to the idea that experience is a structure and every content of experience is a substructure, then it doesn't suffice to have components there. They must be related in just the right ways. And again, an intuition pump is that even if we had a lot of spots, actually all the spots that compose this central region of space, and in this case is white, is bright, we can ask what would happen if they weren't related in the right ways. So if all the distinctions were there, but they weren't related. And again, intuition pump, one way to represent it is that, well, to exploded all these spots across, the visual field in this case, you would have lost the spatial properties of that region of space. You couldn't tell which spot is close to the other, included in the other, what are the distances. You would have completely basically decompose that region. There will be no relations between them. So the idea is that we can characterize a lot of properties of spatial experience. I have already mentioned distance, regions, inclusion, locations, but thorough analysis can be done, and we can focus on the properties that are sufficient to characterize spatial experience, such that all other properties can be derived from these ones. And we call these properties the fundamental properties of space. Again, I point you to the space paper where these properties are described in more details, but just to give you just a summary explanation, I'm going to go through them here in a visual way. So the first property is reflexivity, is the idea that every spot points to itself, which means basically that contrary to time, for instance, where every moment seems to be fleeing away from you, when you hear something is gone, it points to what comes next. Space is there, is very stable. A second property is inclusion, which is that for every spot, there is always a spot that includes it. And if you think about it, this is true, because if you were experiencing spots and there would be no spot that includes a certain spot, then that spot would fill the whole space. But the fact that you can introspect regions of space as being components of the space means that there's other regions that are bigger that include that spot. And similarly, every spot also includes other spots. And that simply means that a spot to be extended needs to include other spots. You need to be able to introspect its left side and right side. Otherwise, it would just basically look like a point. Third property is connection. It is always true that for a typical spot in space, there is another spot that partially overlaps it, and their overlap is also a spot. And then the final property is fusion. It's always true that for every spot, if it overlaps with another spot, there is a spot that is identical. It's basically the union of the two and nothing else. So what I said so far is that the idea of IIT is that there is something it is like to have a spatial experience, irrespective of color, objects, sensory stimuli. Space is as qualitative as color. It's in need of an explanation, just as other prototypical qualia are, such as taste or sweetness. And we can characterize the experience of space in some detail. So that's why we started from the experience of space. In particular, we can say that to experience space, we must be experiencing countless spots, and they must be related in 4 fundamental ways, according to reflexivity, inclusion, connection, and fusion. And from these fundamental properties, the space paper shows that you can derive a lot of other properties that are sufficient to characterize the experience of space in full, not only visual space, but also some sensory space. So what I've done so far was giving you a very brief characterization of how to describe the fundamental properties of space in phenomenal terms. Now the question is, what can we do with the tools of IIT? Can we formulate these properties in terms of cause-effect power? Can we take these phenomenal distinctions and their fundamental relations that characterize spatial experience, and can we find a correspondence in the causal distinctions and relations that compose a cause-effect structure that is unfolded from a substrate that is likely the substrate of spatial experience? So there's a lot of big sentences. So the work has been to characterize phenomenology and take our best guess of what the substrate of the experience of visual space can be. And in this case, we started from grids of units that have lateral connections. And this is based on, of course, some knowledge of visual cortex. We know that visual cortex is, roughly speaking, composed or constituted of layers of neurons that have strong nearest neighbor connections, probably 2D grids stacked one on top of each other. But the idea is that if we can find the fundamental properties of space in the cause-effect structure unfolded from grids, this should hold, even if we simplify, even if we don't have hundreds of thousands of neurons, but we just have, for instance, in this case, 7 neurons. And even if we don't have a 2D grid, but we just have a 1D grid. So what the space paper did was take a grid of 7 nodes, unfold the distinctions and relations, meaning the cause-effect structure would be a substructure of the main complex cause-effect structure, and find a mapping between the properties of phenomenology and the properties of the cause-effect structure. So we're going to go a little bit into the details here, and if you're interested in learning exactly how to compute cause-effect structure, distinctions, and relation, I invite you to consult the wiki. You can find it at iit.wiki, and there are tutorials on how to compute distinctions and relations, and also to go to the tutorial on IIT that Billy Marshall will lead on the 2nd of July as part of the IISSC. So here what you can see is just a little subset of the distinctions that are unfolded from the non-directed grid that I showed before. And this is just some of the distinctions. You can see already that the distinctions follow some sort of pattern. You can see that the mechanism is indicated in black. So for instance, focus on distinction BCD. And then its cause purview is over elements CD, and its effect purview is also on elements CD. So you can see that the cause and the effect purviews are over the same elements, and they are usually a subset of the mechanism. So the idea of IIT is that with no additional ingredients, but just applying the postulates of IIT and unfolding a cause-effect structure, now we can look at the distinctions and the way in which they relate. And we don't need any other ingredient to explain something like space. If the substrate is the right one, we should be able to find a mapping between the properties of, in this case, space, and the relations between the distinctions in the cause-effect structure. So I'm going to focus on 4 spots on the left, just for simplicity. I have described some properties that hold between these 4 spots. And I'm going to take only 4 distinctions from the cause-effect structure for now, just to show that there is a mapping one-to-one between these 2 sets of distinctions and the way they relate. And if we run the analysis, we can find that there is a way to translate reflexivity, which was the first property we highlighted to describe spatial phenomenology, in the way in which the distinctions relate to themselves. So in this case, like I said before, the cause and the effect of every distinction overlap. They are over the same elements, which means that there is a first-degree relation between these in these distinctions. So reflexivity can be found in the cause-effect structure in the way each distinction relates to itself. Similar for inclusion. For every spot, we can find a bigger spot that includes it, and this is also true. For every distinction, we can find a bigger distinction that includes it. In this case, the notion of inclusion is defined by looking at the purviews elements and their state and seeing whether there is a distinction that has a purview that is a superset of the elements of an initial distinction of purviews. So in this case, you can see BCDE again has a cause and an effect over CD. And there is always a distinction, in this case BCDEF, that has a cause and an effect over CDE, such that the cause and the effect of BCDE are a subset of the cause and the effect of BCDEF. So there is a relation of inclusion between these 2 distinctions. This is also true for inclusion down. As I said, every spot includes other spots. Similarly, every distinction includes another distinction, and in this case, it's just the same. There is another distinction whose purview elements are a subset of the purview elements of the initial distinction. We can also formulate connection in terms of cause-effect power now by looking at the way in which 2 distinctions partially overlap. So in this case, just like 2 spots partially overlap, and their overlap is also a spot. In the cause-effect structure, there is always, for any distinction, there is always another distinction that partially overlaps with it. In this case, these 2 distinctions overlap over element D, and there is another distinction that is identical to their overlap. And then finally, we have fusion, which is again that for every spot that overlaps with another spot, there is a spot that includes both and nothing else. And this is always true also in the cause-effect structure. For BCDE, we can find another distinction, CDEF, they partially overlap, and there is a distinction that includes both and nothing else. So this is just a way really to showcase how we can take properties that we characterize in terms of phenomenal distinctions and relations, and we can formulate them into cause-effect power. We can go into a cause-effect structure or substructure, look for these properties, and establish this mapping that now Masafumi we're talking about. So, of course, I've just showed you that these things apply at the level of 4 spots and 4 distinctions from the cause-effect structure. But if we generalize, we want the explanation to hold for the whole space. So these properties that apply throughout the space should also apply throughout the cause-effect structure. And this is true. If we characterize, well, in this case, we can represent every distinction as just a blue node and all the relations as with this code that you see here, we see that the cause-effect structure is a tiling of these properties. And this holds and creates basically a topology. You can describe the relations between distinctions in the cause-effect structure according to these relations of reflexivity, inclusion, connection, and fusion. So as I said at the beginning, we started from 4 fundamental properties that are sufficient to describe space, and from which we can then derive all other properties. Again, I point to the space paper to understand exactly what we mean by that. In the space paper, other properties such as region, location, size, boundary, and distance are uh, accounted for starting from these 4 fundamental properties, so that the identity between the substructure of experience of spatial extendedness and the substructure of the bigger causative structure of your experience, which is in this case just the one contributed by non-directed grids, can be established. Why does this matter, and how can this apply more generally outside of small systems? I think it's important to connect IIT to, of course, the real brain. Even if I personally work with very small systems, I really want to insist that these findings have very big implications. So, for instance, in 2021, we published this paper called "Of Maps and Grids" with Andrew Cohn and Giulio, where we showed the implication of understanding that the quality of space, the extendedness of space, can be found only in the unfolded causative structure of a system. It cannot be found, for instance, in the activity pattern of a system, or just the way in which the system functions. This goes back to Masafumi's example of 2 systems that have the same state, but one has absolutely no connection. In this paper, we did something very similar. We created a system. In this case, it's an eye that has a retina, and it performs some fixation function looking at a screen, and it has a brain where you have 7 units. And in this case, the units can be either form a grid, so having lateral connections, or they can form what we call just a map. Basically, they have no lateral connections, but they can still, with their input and output and activation function, they can perform the same fixation function. So according to an extrinsic analysis, these 2 systems would have very similar activation functions, if not identical, very similar input-output functions. And therefore, we could be tempted to say, well, they both encode some sort of spatial property. They both represent and functions in a way that let us think that they detect space and they can perform spatial functions. But the lens of IIT allows us to see that there is a fundamental difference between these 2 systems. The system which has a grid is actually a system. First of all, there is a main complex, which is the entire grid of 7 units. And when we unfold it, we find a structure that has the properties of reflexivity, inclusion, connection, and fusion that allow the system to specify spatial relations intrinsically. So it's not arbitrary to say, for instance, that when unit B is on and unit C is on, these 2 units are contributing something that is an experience of 2 spots that are close to each other. Whereas, like, if we unfold the map system, first of all, we don't find a single system that has a maximal phi, but it just disgregates. It disgregates into 7 individual systems, and each of them specifies a minimal causative structure that is just one distinction and one relation. And therefore, all the spatial functions are really not grounded in anything intrinsic. There is no intrinsic spatial property or relation that the system is specifying. And again, this, when applied to the brain, also allows us to understand possibly the difference between circuits in the brain that perform very similar functions, such as fixation, but some of them don't basically happen in the absence of conscious experience, such as some subcortical circuits. And some of them instead do contribute to conscious experience, such as the ones indicated here in blue that involve cortical pathways. So this, of course, ties back to the fact that for IT there is a dissociation between function and phenomenology, and Graham will talk more about that. And it also ties back to the idea that studying the experience of space and accounting for the experience of space in terms of its substrate and the unfolded cause-effect structure allow us to make also predictions about the substrate and the lesions and how exactly the experience of space can be impaired. And I believe Giulio will say something more about this.
Just a few things. So I hope, the overall idea here got through. Okay. Above all, realizing the obvious, which is not obvious at all. It's one of the most difficult thing apparently for people to understand. That for space to feel extended, about color and objects and other things, it must be an extraordinary structure composed of distinctions and relations of a certain kind. And what was shown is that if you have a substance, namely grids, and you unfold it with no additional ingredients, you can account for those very properties, that is, for the quality of space feeling extended. I will point out one more thing here, which is we chose space, as they say, because, first of all, most of our experiences, not all, happen in space. Now, the space of experience is much, much, much richer than what was illustrated here with just a flat 2D screen. Okay, we have depth, there is body space, there is the fact that you're in the middle of this space, there is the space that surrounds you in the environment, which you're also aware. So the real space of experience is an incredibly rich composition of this fundamental spatial aspect. It shows one that is pervasive, it's everywhere, essentially, literally. But also we try to go down to its simplest manifestation, so to speak, and even its simplest manifestation, like an extended campus, is incredibly rich, if I think so. The second thing to say about this is, and that's why we started there, is that space is, we say, penetrable, cognitively, introspectively. So for space, unlike for blue, as I said, you can actually use what is called the spotlight of attention or spatial attention to move around, sort of single out spots, and then see that you have small and large here and there, and they point themselves, include each other, partially overlap each other, fuse with each other. So all of this you can do quite easily. It's the most natural thing we do. But it is a cognitive function that requires attention, introspection, etc., which we can apply to space to dissect a little bit its structure. So phenomenal distinctions, like spots, and relations, the way they sort of overlap. For other things, this is not doable or much more difficult. Even for time, it's more difficult. For objects, it's more difficult. And for things like color and touch and itch and so on, it becomes progressively more complicated, if not undoable. But for space, it is, which is why we started there. The second thing to say is that you saw this map and grid, okay, pointing already to the brain. And I just want to point out, because it comes out every time, you might have come out with the questions, a typical thing that you will find about OIT's got a problem is a quote to an old article or blog by Aronson, Scott Aronson, that somehow, became sort of widely read without really reading much of the response to it. And Scott Aronson's point is, I think, very indicative, okay, because he was saying, wait a second, I can sort of show that basically a grid. He did first the mathematical equivalent of that, but he realized that he had to be a physical thing, so I agree. Can have high phi, so potentially could be ultimately a complex of high phi. In fact, potentially make it very, very big with very, very high phi, and therefore with a fantastic phi structure, cause-effect structure. And that's obviously nonsense. One might say bonkers. So is that true? And so his intuition was, of course, like that of many people, that if you can get consciousness out of grids, that's so silly that obviously why the theory he appreciated was mathematical, testable, and all the rest, which was hard to find. but obviously it's bonkers. The response, and in reality, the true response is still going on because it's the difficult work of actually unfolding these things and pointing to their phenomena and causal equivalence, and then to the brain and testing it. The response is, for instance, contained in this slide that was made by Chen, there, quite a long time ago, that actually say, among other things, to Scott Aronson, that lo and behold, we are primarily grids. That is, the subset of consciousness that we've seen this morning is largely in posterior cortex, and posterior cortex is, of course, not just grids, but it's fundamentally a bunch of grids stuck on top of each other, connected in complicated ways, and then with hierarchical aspects in it. But there where the evidence points to the subset of consciousness is a bunch of grids. 1, 2. Most of our experiences are spatial visually or spatial on the body. So if you actually look at the evidence, which has been there, this evidence has been there forever, okay, it fits a lot, both phenomenology and empirical data about the subset of consciousness in the brain, that the Humboldt grid, okay, a bunch of Humboldt grids, if they have big fan in and fan out and some other properties, are actually an ideal, near ideal substrate for a rich experience once you understand the space is rich. So far from being a problem, it's a feature, it's not a bug. And we say this from the start, but always know the old paper 2.0 on a grid is a very good substrate in principle. It's not enough to be a grid, but it's a good substrate. And I want to point this out because this is normally presented as much of cortex, this is neuroscience 101, is organized topographically. And topographically, back to the previous picture, really means something like a map system. That is, you take points in outer space of the body and you project them, you map them onto some neurons, and you see that what close out there is close in here. And that's the very first thing that people did, in a way, in neuroscience. But that is not enough. What you need is a grid for which space is there intrinsically. It's not a representation of something out there or a function towards something out there. It exists because of what the substrate truly is once you properly unfold. And then if you look at these, don't call them maps. I mean, you can, but think of them as grids, okay? Because when you dream, for instance, disconnected from the environment, space is wonderfully there, just as rich, with things left and right, top and bottom, small and large, here and there, okay? It's all there, just in the same way. And it doesn't map anything, okay? It is a bunch of grids. Interestingly, primarily posterior cortex. And here's some additional evidence. This is a subject I like to quote because it's a study on a lady who underwent an occipital lobectomy. You can see it there. So they took out a piece of her occipital lobe on one side, and they knew they were going to do it. And one thing they did is they tested her in various ways. But one way was to ask her, and this was a test of actually Koskin's idea about the neural subset of iman. So it was a test of imagination, not of visual consciousness or space. They asked her to imagine various things like a horse or a car, etc., and wonder, when it would be close enough, make it come closer and closer and closer, that it would completely fill her visual field. And then it started overflowing. And she said, for instance, gets, within 15 feet. And then, it was overflowing, things like that. And then they did the surgery. They took out basically one set of visual areas in one half of her brain, in one hemisphere, and asked her the same questions. And basically, no matter what they did, it turned out that the horse was filling her visual field when it was much smaller, so to speak, much more distant. Okay, roughly twice as necessary. And the interesting thing to always think about in this case is that she didn't complain at all. She just told them, where it was, when it overflowed. So these patients typically do not complain that their visual field has shrunk. the space has shrunk. This is another thing consistent with IIT, that if you lack the substrate, it just doesn't exist for you. It's not that you're missing something and you feel it and it's bad. You're just fine. This is the same that happens with split brain patients, by the way. Okay. The left guy doesn't realize that he has lost half of the visual field, or a big portion of the visual field. So was this lady. And so this was sort of tested explicitly. And this actually has, various other interesting ramifications. One of these is being tested in a second Templeton adversarial collaboration, which is, IIT on one side and, predictive processing on the other side, more or less. But the idea here is not take hemispherectomies or so, which are sort of rare, but take patients who have cortical scotomas, meaning they lose a piece of visual cortex. As a result of that, they become blind in that scotoma. That's what scotoma means. They are blind there. But the point, which is often sort of not even discussed in the neurological literature, is that unlike, say, retinal lesions or so, yes, they are blind in the sense that they don't see objects that happen in that blind field. But the difference, we think, is they don't actually feel that they are missing something. That space literally disappears from there. They just don't have it, just like the lady, only to a smaller degree. And so in principle, this is testable by measuring, where they think space ends, speaking in various ways. This is very complicated again because we have many visual areas, etc. But that's the idea, that the experience itself changes. To take away a piece of the grid, a piece of you is gone. Not because you don't map the visual world out there, because space doesn't exist for you and everything attached. So finally, I want to also point out experiment done by Chen Song here in the front, which has many limitations, not Chen, the experiment, okay? Many limitations, but it is a fundamental step, I think, in the right direction. One of the key predictions of IIT is that if you change the strength of connections in the subset of consciousness without changing the activity pattern, you are going to change the way the experience is. So activity pattern the same, everything is the same, but you happen somehow to have changed the strength of connections. You should change the quality of the experience. And so again, because we try to test this simply on space, using a trick, and again, there may be objections about exactly what's going on. We don't know that for sure. Multiple areas are involved. But the idea was to have a testing phase in which you show bright dots and you judge how close they are, let's say. And then you have a training phase and then testing again. And the training is applying bright spots flickering very rapidly to induce, as we know from some other experiments, strengthening of connections. And if you do it at the right distance, where we know there are lateral connections in the visual cortex there in the middle, then you should be able to strengthen connection there. If you do it too far away, there are no connections, so you don't strengthen anything. Okay? So you do this, assuming you've got what we think might have gotten, the strengthening of connections there through this training phase, then we repeat the test and we ask them to judge how far apart two bright dots were. And what turns out is that the space contracts a bit in this case. So they judge them to be closer, even though presumably the activity pattern that we induce is the same as this, because, for instance, the critical experiment, we lighten up the two far away dots where we didn't produce any strengthening. We only produced strengthening in the middle, so to speak. And yet they feel close. So this is directly in line with the prediction. And I think there are many more experiments of this, especially in the line of what Now and Masahumi showed, including the development of the experiences and their quality, should be pursued. It was very nice to see the children, okay, and trying to map the similarity of spaces in the children in dependent language. Because on the other hand, for instance, when you learn Japanese or you learn English, one key thing is, and we expect, because the number of neurons doesn't really change, that in some cases activity patterns may be the same, but after training, listening a lot to Japanese vowels and so on and so forth, as we know happens, then the quality of what you feel, and therefore its measurability, may change ideally to make the conceptual point without the activity pattern change. So there are actually lots of experiments with some imagination, and of course with the complexity of the brain, but nevertheless, that's what art is in doing science. With some imagination, one may be able to test this idea that experience changes in a predictable way, even though the activity may be the same, which is definitely, not the rule. So I will leave it at that to move to the second attempt that also took a long time. The paper is coming out very soon. That was done by Renzo and Matteo. And Renzo will, in a short time, give you at least the gist of the same approach applied to trying to explain why time flows.